Okay, we're going to finish our lesson with stretching and shrinking functions. Remember, shrinking can also be called compressing. Stretching or shrinking a function's graph changes its size but does not change its shape, position, or orientation. So in example 3, I have two graphs and some tables. So given each function graphed with its parent function, fill out each table to help describe the stretch or shrink applied. Okay, so letter A is g of x equals 2 times the absolute value of x. So we know the parent function is f of x equals the absolute value of x, which is graphed for you. And then we have g of x equals 2 times the absolute value of x graphed on the same graph. I mean, just naturally, what we said something like this looked like, it looks skinnier. But I'm thinking about stretching and shrinking. If it's getting skinnier, you could think it's shrinking inward, or if it's stretching, if you want to describe that as a stretch, it could be maybe being pulled upward, maybe vertically. Let's see what happens with our values in the table to help us describe it. Okay, so I'm going to fill out this table. We did something like this earlier. If we just did the inputs -2 to +2 like we did earlier and filled out y equals the absolute value of x, we remember what those are. That would just be +2, +1, 0, 1, 2. And those are the points that are plotted here on our graph. Now, what happened to those points if I put a 2 in front of the absolute value of x? What it means is I'm taking this 2 and I'm multiplying it times this column. So that's 2 times 2, that's 4. That's 2 times 1, that's 2. That's 2 times 0, 0. 2 times 1, 2. And 2 times 2, 4. Which are plotted here. 0, 0. You can look here. 1, 2, 2, 4. See those? 1, 2, 2, 4. Okay. So what is the relationship between our two outputs of our functions? What we have done, as you can see, for every output in this column, to get the new ones, we multiplied by 2. We multiplied the output, the y-coordinate, by 2. So the y-coordinate is multiplied by 2. What that does is it stretches it upward. So we see, let me just get different color here. This point moved up here. This point moved up here. This one moved up here. This one moved up here. You can also see that their change in y values doubled. So this was 1 unit above the x-axis. This is 2 units. This was 2. Now it's 4. So what we call that is a vertical stretch by 2. Because this is a 2. And we're multiplying it times the y-coordinate of the parent graph. Now, it's vertically stretched, so I like to think of maybe grabbing like some Play-Doh. And obviously, if you stretch it vertically, pull it upward, it's going to get skinnier. So that's why our eyes are like, oh, that looks skinnier. But that's because it's been pulled upward vertically. So maybe that helps us look at B and explain that with a better word than, oh, it just looks wider, okay? So h of x equals 1/2 x squared. Let's fill out the table similar to what we did with our absolute value one. We see the parent graph f of x equals x squared. Remember, we just square all these values. This is 4, 1, 0, 1, 4. And then this means we're going to take 1/2 times x squared. 1/2 of 4 is 2. 1/2 of 1 is 1/2. 1/2 of 0 is 0. Half of 1 is 1/2. Half of 4 is 2. And these are these points, 0, 0, or we can start here, -2, 2. See, -2, 2. -1, 1/2. That's right here, 0, 0, 1, 1/2, 2, 2. When they used to be -2, 4. -1, 1, 0, 0, 1, 1, 2, 4. So now my vertical distance is half of what it used to be. So we multiplied each y coordinate by 1/2, and what that resulted in was a vertical shrink by 1/2. So we stretched in A because that number we multiplied by was greater than 1. So you multiply something by 2, you're doubling it. In B, we multiplied by 1/2, so we're cutting it in half. And so if we're vertically shrinking, take that Play-Doh again and vertically shrink it, it means smush it down, it's going to get wider. So that's why we saw that wider in there earlier. Okay, we're gonna try this out. Identify each function's family and the stretch or shrink applied to the parent graph. Remember, if that number in front is greater than 1, it'll stretch. Less than 1, it'll compress. So g of x equals 3 times x squared. X squared is a quadratic. That number is 3. 3 is greater than 1. This is a vertical stretch by 3. B, we have h of x equals 3/2 x squared. Again, we have x squared. That's a quadratic. 3/2 is 1.5, which is greater than 1. So this is also a vertical stretch by 3/2. Finally, we have C. C of x equals 0.2 times the absolute value of x. Ooh, absolute value is our family. 0.2 is also 2/10 or 1/5, which is less than 1. So this is a vertical shrink by 0.2. Okay, I'm going to quickly do these last 3 problems. They have multiple transformations because you can put more in one function. I'm going to breeze right through it. If we just review quickly, these stretches happen by multiplying in the front. So in letter A, I have a 1/4 out front of this absolute value. And that 1/4 is less than 1. So that's going to be a vertical shrink by 1/4. Then remember when we added or subtracted inside the function, it was moving right or left, and we had to think opposite for that. So that is going to actually move left 5. Letter B, do you remember what a negative in front did? That did a reflection over the x-axis, and this is a squared, so this is quadratic. That negative sign reflect over x-axis. We're adding 9 up at the end. That will move us up 9. Finally, 4 times the absolute value of x minus 1. Just another absolute value. The 4 out front is being multiplied by the function, and 4 is greater than 1. So that's a vertical stretch by 4. Inside my function, I have x minus 1. Outside, I have plus 3. Those are translations because they're being added or subtracted. The minus 1 is going to move us right 1. The plus 3 is going to move us up 3. Now, don't feel like you have to have all these memorized, but at least you have an idea how we can see translations, reflections, and stretches and shrinks, and we'll talk more about it in class tomorrow. Have a great night.